Let's talk about something that you can't see but is literally everywhere. I'm talking about pressure. It's the force in the air we're breathing right now and the water in the ocean. But how in the world do you measure something you can't even see?
Right. It's in the air, inside your tires. It's in the deepest parts of the sea. Pressure is a constant. So if you're an engineer, how do you build a tool that can accurately measure the push of a fluid? Well, the answer starts by thinking very, very small.
To get our heads around the big picture, we have to zoom way, way in. We're going to start our whole investigation at a single microscopic point, just hanging out inside a fluid.
Seriously? Just picture it. A tiny little speck, just floating there, completely still. It could be in a glass of water on your desk or in the air in this room. The key is it's not moving. It's perfectly balanced. And because it's sitting in a fluid, that fluid is pushing on it. You've got forces acting on this tiny point from above, from below, from the sides, from absolutely everywhere all at once.
And this brings us to our first huge fundamental rule. It's called Pascal's law. And all it says is that for a fluid that isn't moving, the pressure at any single point is exactly the same no matter which direction you look at it from. The push from the left is the same as the push from the right is the same as the push from above. It's really as simple as that. If you could shrink down with a tiny pressure gauge and stick it right on that point, you could aim it up, down, sideways, diagonally, it doesn't matter. You'd get the exact same reading every single time. This one idea is the bedrock for everything else we're going to build on.
Okay, so that's the rule for one tiny little point. But what happens when we zoom back out and look at a whole body of fluid, like a swimming pool? A couple of really simple but incredibly powerful rules pop out.
All right, let's break this down. It's easy. First, if you move along any flat horizontal line inside that fluid, the pressure stays constant. It doesn't change. Second, as you move vertically, as you go down deeper into the fluid, the pressure increases. Makes sense, right? There's more stuff on top of you, pushing down.
This is the perfect way to think about that horizontal rule. Imagine you're in a swimming pool, let's say 2 feet under the water. If you walk all the way from the shallow end to the deep end, but you stay exactly 2 feet below the surface, the pressure on your body doesn't change one bit.
Now, there are a couple of gotchas here, 2 really important conditions for this to work. First, the fluid has to be continuous. You have to be able to get from point A to point B without leaving the water. And second, you have to stay in the same fluid. If you have a layer of oil on top of water and you cross that line, all bets are off.
So with these super simple rules in our back pocket, pressure is equal at a point, it's constant horizontally, and it increases with depth, engineers came up with a really clever little device to measure it. It's called the manometer.
I mean, think about the problem they were facing. If you just stick an open pipe on a high-pressure water main, the water could shoot 70 feet into the air. That's not practical. You can't ask a technician to climb an 8-story ladder just to read a pressure gauge.
The solution is this genius U-shaped tube, the manometer. To understand how it works, we just follow the path. So we start inside the pipe, at the pressure we're trying to figure out. Then we travel down into the heavy liquid in the U-tube, something like mercury. And as we go down, what happens? The pressure goes up.
Okay, now we're at the bottom of the U. We're going to scoot horizontally across to the other side. And hey, what was our rule about moving horizontally in the same continuous fluid? That's right. The pressure is exactly the same. It doesn't change a bit.
So boom, we now know the pressure at that spot on the other side of the tube. From there, we just travel up toward the open end, which is just open to the air around us. And as we go up, against gravity, the pressure decreases until we hit the end, which is at atmospheric pressure.
And that's it. By adding pressure as we went down and subtracting pressure as we came back up, we can write a simple little equation that lets us find that unknown pressure we started with. We totally just used basic physics to solve a massive engineering headache.
All right, so we figured out how to measure pressure, but now we need a way to talk about it. And it turns out different fields have come up with their own kind of languages to describe the very same force. Let's just take standard atmospheric pressure, the pressure of the air around us right now. You could call it 14.7 pounds per square inch, or PSI. But a meteorologist, they might call it 30 inches of mercury. A scientist might say 760 millimeters of mercury. And an HVAC engineer could even talk about it as 34 feet of water. They're all talking about the exact same amount of push.
And what's so wild is that these units are just different ways of talking. It doesn't mean there's actually water in your car tire. It just means the pressure, the push inside that tire, is equivalent to the push you'd feel at the bottom of a column of water that's 34 feet deep. It's just a language of comparison.
So why do we care about all this? Why does understanding these principles of pressure matter so much? Well, because they let us reliably and predictably build things and interact with the world all around us.
Think about the journey we just took. We started with the microscopic truth of Pascal's law. That led us to the simple rules for a whole body of fluid. And then we saw how those rules led to the invention of the manometer, this clever tool that turns an invisible force into something we can actually see and measure. It's a perfect example of how the most basic ideas can lead to really powerful tools.
By understanding the physics, we can measure what we can't see. And it kind of makes you wonder, right? What other invisible forces, from electricity to gravity, are we constantly measuring every single day, with tools built on equally simple, elegant rules? Something to think about. Thanks for tuning in.